Hello everybody, it's Mr. Ray here with our next lesson in calculus. Um, we're actually we're gonna be skipping a few lessons that we would normally do in the course just for the sake of time and in order to do the most important stuff. So in Unit 6, we're actually gonna skip lesson 2, which was sketching derivatives. It's kind of a good exercise, but in the long term, there's a lot more important things that we have to cover. So this lesson here is called Derivatives of Polynomial Functions. And to me, this is where the true calculus course starts. Okay, obviously very important to understand what a derivative is. And as a reminder, in case you've forgotten, it's a mathematical function that gives the slope of a tangent at a point along a given function. So and that slope of the tangent is also the instantaneous rate of change. Okay, so instantaneous rate of change, slope of the tangent, derivative, basically all means the same thing. Okay, but the function, the math part, the actual function part is called the derivative. Okay, so we're actually going to be looking at polynomials, and at the same time we're also going to look at radical functions, anything like a square root or cube root or fourth root. So any function that's got any kind of root or any kind of integer exponent. It could be multiple terms. So that's what we're going to look at today. So there's a few rules here, and this is the kind of the basis of what we're going to be doing today. Now you don't have to memorize these rules. To me, these are all combined into what we'll be doing in each example. So basically, but it can be broken down this way. So if you have a constant function, for example, f of x equals a value like 7 or negative 22, where k is a constant, then the derivative function f prime of x is always equal to 0. And that should make sense, because if you had a constant function and you graphed it, well, that's just going to be a straight horizontal line. Okay, and if you're asking, well, what's the slope of the tangent at any point along here, or what's the instantaneous rate of change? Well, it's not changing at all. It's always 7 or negative 22 or whatever the function says. So whenever you have a constant function, the derivative function is always 0. Okay, now this is again, function notation, which we learned in grade 11 and advanced functions. So the derivative function using function notation, that's where we call it f prime of x. The original function was f of x. We have this thing called Leibniz notation. Leibniz is a famous mathematician who's basically the father of calculus. So I guess we name a lot of things after him. So this notation, the way we can read this is the derivative with respect to x of k is equal to 0. Okay, so that's another way of just saying f prime of x is equal to 0. So that's the Leibniz way of saying it. And this is the function notation way, but you can see we have a 0 on both sides. Okay, now the power rule. So basically, if you have a function f of x which is equal to x to a power where x is an integer. Well, actually they say real number here, so I guess we could bring in fractions, which are really radicals, like square roots and cube roots. So if you have x to any power, and this could be negative, it could be a fraction, obviously could be positive, could be integers, pretty much anything. Okay, and this is the key thing for today. So what you do, if you're taking the derivative of x to the n, what you do is you take the exponent n and you bring that out and multiply it as a constant in front of the function, like a coefficient. So that comes out front as a multiplier, and then you reduce the exponent by 1. Okay. Once you see some examples, it'll make much more sense. But basically, this is a key thing for today. So the function notation f prime of x is equal to a times x to the n minus 1. And we've got the same thing here. Or sorry, that's n times x to the n minus 1. And we got the same thing over here with Leibniz notation. So this is the derivative with respect to x of x to the n is equal to that. Okay. If you have a constant multiple rule, okay, so basically it's a lot like what we had up here, but if the function has a coefficient in front of, in front of the power function, the derivative function is k times g prime of x. So basically you'll take the derivative of g to the x, and whatever that is, whatever the derivative is there, you multiply it by k, and that's the derivative of f of x. Okay. Again, it'll make a lot more sense when we do some examples. And you can see we're just pulling, you can just basically pull that k out front in that case. Okay. And then you have sum and difference rules. So this is like if you had if you had a function that was made up of the sum of two other functions, well, that's simply the overall derivative is the derivative of p plus the derivative of q. Okay. And same thing with difference. The only difference between these two was the sum changes to a difference. Okay. So here's where we can start doing some examples. So determine the derivative of a simple rational function, such as f of x equals 4 over x to the 6. So this is basically when you have like a negative exponent, or x to a power that's, you're dividing by that. So the rule is, or the technique is always express the function as a power and then use the power rule. So basically 4 over x to the 6 is the same as 4x to the negative 6. So this became like a power function with a coefficient out front. Okay, so once we've changed the way f of x looks so that you've got it looking like that, then you just use the power rule and the constant multiple. So the way that works, you take the negative 6, which is your exponent, you bring that out front of the whole thing. So it's negative 6 times 4, or 4 times negative 6, doesn't really matter the order. And then you reduce the exponent by 1. So if that's negative 6, if you reduce the exponent, that becomes negative 7. Okay, so be careful with that. If that was a positive 6 and you reduced it, it would be 5. But 1 lower than negative 6 is negative 7. So negative 6 minus 1 is your new exponent, so that when you multiply these two together, negative 24x to the negative 7, and then we always fix the negative exponent, put it back under the division bar. Okay, so the derivative function of f of x, f prime of x, is equal to negative 24 over x to the 7. Okay, and if you start off with a radical function such as g of x equals the cube root of x to the 5th, we want to rewrite this with a rational function. So that would be the same as x to the 5/3, and then we just use the same rule as before. So we take the 5/3, which is our current exponent, we bring it out front, like we did here, and then we reduce the exponent by 1. So if I reduce 5/3, by 1, that's like 5/3 minus 3/3, which gives us 2/3. Okay, so that's the answer, and then we change it back to radical form. So x to the 2/3 is really the same as the cube root of x squared. So we just fix that. Okay. All right. So this one here, we're just looking at a couple of constant functions. So we have f of x equals 5 and y equals pi by 2. These are both constants. These actually never depend on x. Pi by 2 is a constant, even though sometimes pi looks like a variable. It's not. Okay, so these are constants. So for this one here, we can write f prime of x, and anytime the original function is just a constant, the derivative function is always 0. Okay. Um, this one here, um, we could, again, that's a constant, so the derivative of this, we could write it a couple ways. We could say y prime is equal to 0. Okay, because this time it's not function notation, it's just a variable equals. So we could say y prime, or we could say the derivative of y with respect to x, dy by dx, or dy by dx, is equal to 0. So that would be two ways of saying that. And this would be the answer. So basically, anytime you have a constant function, the derivative function is 0. Okay? All right. So let's go to the next examples. There's a few of them here. So this is where you'll get your technique very quickly with these examples. All right, so we have f of x equals x to the 7. So find the derivative of each of these. So, that's going to be f prime of x is the derivative function. So what we do, we take since this is only one term, the 7 comes out front as a multiplier, so it's 7x, and then we reduce the exponent in the original function by 1, so it's 7x to the 6, and we're done. Okay, this one here, so g of x equals 1 over x cubed, so we really should fix this, so that's the same as x to the negative 3, and now we can do the derivative, so g prime of x. Now this time bring the negative 3 as a multiplier at front, x, and then we reduce the exponent by 1, so again, if it's negative, it's like negative 3 minus 1, which is negative 4, and we want to fix any rational or negative exponents, so that would be the same as negative 3 over x to the 4th. Okay, so hoping that makes sense to you. Let's try this one here. This time we have s equals t to the 3/2. Well, that's already in the right form for us to use. So we could write this as s prime, or we could say derivative of s with respect to t, ds by dt. Okay, so again, that exponent becomes basically the coefficient or a multiplier out front, so that's 3/2 times t. Now we reduce the exponent 3/2 by 1. Remember, 1 is the same as 2/2, so it's 3/2 minus 2/2, so that's a new exponent 1/2. Okay, and we want to fix any rational or negative exponent for our final answer, so t to the 1/2 is just going to be the square root of t, so we could leave it that way, or we could say 3 root t over 2. Both of those are totally acceptable. Okay, what if you had something simple like just y equals x? So you could say y prime, since it's just a variable, not a function notation, y prime, or you could say dy by dx. Okay, so if you think about it, that exponent there is really a 1, even though it's not shown. So we could still use the same rule. So that becomes 1 times x, because the 1 comes out front. And if we reduce that exponent by 1, it's actually 0. But anything to the power 0 is just 1. So this really just becomes 1. So if you think about it, the line y equals x, that's that's a line with a slope of 1. Okay, so what's the rate of change of that function, or what's the derivative of that function? Well, it's always going to be 1, because 1 is the rate of change, which is the slope in the case of a linear function. So in this case, that gives you the slope of the line everywhere. Okay, if I had y equals 2x, the derivative y prime would be 2. If it was negative 3x, the derivative would be negative 3. So when you don't have when you have a term that's just x to the 1, the derivative of that will always be the coefficient. Okay. Okay, so let's make it slightly more complicated. We're going to have some coefficients of the original function. So this time we have f of x equals 7x cubed. So the derivative function is going to be, we take the 3, which is the current exponent, we bring it up front, multiply that with the 7 that's already there, and then the x and the exponent gets reduced by 2, gets reduced to 2. So then we have 21x squared. Now you don't have to do that step, you can go directly to there, but basically I'm showing you that that 21 comes from the 3 times the 7 in front, and the exponent for x gets reduced by 1. Okay, this one here is g of x is 12x to the 4/3, so that's already in a good power function terminology. We don't have to change it like we did with some of the earlier examples. So this g prime of x is going to be, now I'll do it the long way, you don't have to do it this, so the 4/3 comes out front and gets multiplied with the coefficient that's already there, so that's a 12, and then the x, the exponent gets reduced by 1. 1 is the same as 3/3, so 4/3 minus 3/3 is 1/3. Okay, so we can clean this up. Basically 4/3 of 12, that's 48 divided by 3, that's 16. And then x to the 1/3, we would always change that to a radical form, so that would be cube root of x. So the derivative of 12x to the 4/3 is 16 times the cube root of x. Okay, let's just try a few more. Should be a fairly quick lesson here. Okay, so now we're going to introduce like some multiple terms in the function. So far we've just been looking at single term functions. Okay, so if you have multiple term functions, it's handled really the same way as before. Just remember, we'd be taking the derivative of this, and then we subtract the derivative of this, and that would be the derivative of f of x. So f prime of x. So we just really treat these as separate functions. Okay, so here, do this one a little quicker. That's going to be 2 times 3 times x to the 1, so that's just 6x, and I'm going to keep my negative sign there. Now I guess I should have written this to get rid of the radical sign. So square root of x is just x to the 1/2. So it's always good to write it this way. Then you can do your, it's much easier to do the math with, you need to know that you multiply by a half and then you reduce that 1/2 by 1. So if I'm looking at this part now, we've already done the 3x squared. Its derivative of that is 6x. We have the minus sign from here, and then the derivative of 5x to the 1/2, that's going to be 1/2 times 5, and then the x is going to be to the power of negative 1/2, because a half minus 1 is negative a half. So let's clean this up. So that's already done here. So that's going to be minus 5/2, and x to the negative a half, that's going to be, well, I could write it like this. I could bring this down here, x to the 1/2, to at least fix the negative part, and then finally I'll just convert the 1/2 to a square root. So 6x minus 5 to root x. And that would be your, well, I've kind of gone into the next question. Okay, so this would be your final answer. Okay, now this one here, we haven't really learned how to handle when the exponents for a binomial expression. Okay, we're actually going to be learning this the next lesson. We're going to use something called the chain rule that will tell us how to directly differentiate this. But for the time being, what we're going to do is just expand this. So that's going to be 9x squared, and that's going to be 12x plus 12x plus 4. Okay, so now I'm just going to handle it as a polynomial with, each individual term we're going to differentiate. So in this case, y prime, or dy by dx. Now you don't have to do both of these. I'm just showing you that they both mean the same thing. That's going to be equal to the derivative of 9x squared, so that's going to be 18x, plus the derivative of 12x. So remember that case, we talked about this earlier. So if that's a 1, you get a 12 up front times x to the 0, so it's just 12 times 1, so it's just plus 12. And then you have the derivative of a constant, which we already know that derivative of 4 is 0 because there's no change at all, it's always 4. So that will be your final answer here. Okay, but like I said, our next lesson, we're going to learn about the chain rule. We could actually do this a different method. In this case, it's probably quicker to expand it, but what if you had something like 3x plus 2 all to the power of 5 or 6? Certainly don't want to expand something like that. Okay, so next lesson we'll be doing that. All right, this example, using derivatives to find the equation of a tangent. So it says, determine the equation of the tangent in the graph of f of x at the point x equals 1. Okay, so what we're going to do here, I'm going to do the derivative function first, so f prime of x. So I go back and look at this, so that's going to be a 3 times negative 1, so that's negative 3x squared, reduce to 3, that's going to be plus 6x, and the derivative of minus 2, that's 0 because it's a constant, so that's the derivative there. Now this is where we want to take the derivative. Now eventually we're going to need to know that point, you'll see in a second. So if you plugged in, if you did f of 1, like plug in the value 1 here, you're going to get 0. So that's really the point 1, 0. So we're going to get the slope of the tangent, equation of the tangent at that point. Okay, so we've already got the derivative function, and it says determine the equation of the tangent at x equals 1. So now we just plug in f prime of 1. We're setting x equal to 1 because that's where we want to find the slope. Okay, so that's going to be 3 times 1 squared plus 6 times 1. That is going to be 3 plus 6, which is 9. Oh, is that right? No, that's a negative 3. So, yeah, I got to go back and fix that. That's a negative 3. Okay, so when I plug in 1 here, I get negative 3 plus 6, so that is just 3, not 9. So that's the slope of the tangent at x equals 1. Now, they didn't just want the slope, they wanted the equation. So basically that tells you that the derivative function gives you the slope of the tangent. So that basically tells you that the slope in our tangent equation will be 3. So from there we can start building the equation. That's y equals 3x plus b. And this is where we're going to sub in the point 1, 0 to get our b value. So that's x equals 1, y equals 0. So that means b is going to be negative 3. Okay, so once we've got that, then we can just go back and create 3x plus b, or 3x minus 3 is the slope of the, sorry, it's the equation of the tangent. So I'll just put that out front here. Therefore, equation of tangent at x equals 1, is that. Put a box around. Okay. All right. Here's a slightly different one. Determine points on the graph from the graph in example 5. So it's using this function f of x up here. Find the points where the tangents are horizontal. So when the tangent is horizontal, you have to interpret what that means. That means, you have something like this. Tangents are horizontal means the slope is 0. Okay, so that's important. Now, if the slope is 0, that means the derivative is 0. Okay, so that means we can go back to our derivative function here. So I'll just repeat it. Negative 3x squared plus 6x. Okay, but now we know the actual derivative. We want to find where the derivative or the slope is 0, so we can plug 0 in here. Okay, so this is basically a quadratic, and we're trying to find the values or solve for x here. So if you remember from previous math classes, you can do this either by factoring and solving, or you can do it through the quadratic formula. Now this one is pretty nicely factorable, so I'm going to factor the negative 3x out, and I get negative 3x minus 2. So we get two values of x that'll make this true. X equals 0 and x equals 2. Now, we're not quite done because it says determine the points. It doesn't say just determine the x values. So now we got to go back and plug in x equals 0, not in here because this is the derivative function. So I'll make it very clear. We need to know what f of 0 is. So if I plug that back in to the original equation back here in question 5, that would mean f of 0 is negative 2 because both of those terms are 0. And f of 2, if you plug 2 into there, you're going to get f of 2 equals 2. So basically these are the points 0, negative 2, and 2, 2. So to answer in words, therefore the points 0, negative 2, and 2, 2 have horizontal tangents. Okay. Now this is going to come in important later on in the course, because when you have a horizontal tangent, most of the time it's going to mean that it's a point, it's going to be a maximum or minimum because you're changing your direction from increasing. Your function is increasing, changing to decreasing, or vice versa. There's some other cases where the tangent is 0, but you can see that this is going to be an important process later on. Setting the derivative function to 0 will allow you to find maximum, minimum points or extrema points. Okay. Now, hopefully this was a fairly satisfying lesson. Like I said, all the stuff that we did on the previous lessons, for example, let me go back to the first page. I'm on a multiple term one. Okay, so if I had given you this before today and asked you to find the derivative, you would have had to use first principles, the limit as h approaches 0. That's a major pain, but you know how to do that now, so you know how it works. So now when I ask you to find the derivative, you don't have to do it from first principles, you do it from basically the derivative laws that we're learning. Okay, so you can go directly from the function to the derivative pretty much. Okay, so that should be nice to know that you don't have to have those half-page calculations to go from here to here. Now you can just do it very quickly. Okay, so like I said, the next lesson will be looking at something called the chain rule, where we can take something like a binomial to a power and find the derivative fairly quickly. Okay, so got some homework questions at the bottom here. Try some, make sure you're able to do this. But I think this homework should go fairly quickly. There's some more challenging questions at the end there. Hopefully, if you know what you're doing, you can get those too. Okay, so we'll do one more lesson this week. I'll probably put it out Thursday afternoon. And then the assignment this week will be based on these 3 lessons. Okay, so have yourselves a good day, and we'll see you on the next lesson.